Our next speaker is Agustín Gravano. He's from Universidad de Buenos Aires in Argentina. And let's wait some seconds, please.
Hello. Okay, hi. I hate the other microphone. First of all, I would like to thank the organizers. This is a wonderful school, really, so thank you. My name is Agustín Gravano. I'm a professor at the Computer Science Department at the University of Buenos Aires, just across the river. And I'm also a member of the Applied AI Lab, the LIA, which has grown a lot in the past few years. And we do research on several topics, including computational neuroscience, computational psychiatry, natural language processing, and speech processing, and many others. And I wouldn't have time to go through all of them, so I chose to focus on the speech processing topics. So I guess everybody here must be familiar with some of these modern virtual assistants. We have them in our phones, in our home maybe. To mention a few, the most famous ones, Google Assistant, Microsoft Cortana, Amazon Alexa, and Apple Siri, placed here in no particular order. These are great products, I guess we all agree with that. They appeared after the beginning of the success of automatic speech recognition technologies. That was around 6 to 7 years ago. So this is moving pretty fast. And this was thanks to deep learning, of course. I was saying these are great products. They are useful for performing various tasks, ordering pizza over the internet, arranging meetings, playing music. And we can do all of this with our voices, right? However, in terms of dialogue, the interaction is quite basic still. This is very far from the complexity of human dialogue. It's even kind of embarrassing to call these assistants actually spoken dialogue systems, because there isn't much dialogue really going on. It's mostly simple comments and very short interactions. We definitely would like something more than this in the future. So what would we like future virtual assistants or robots to be like? Well, to begin with, I guess we'll agree that we would expect to have these systems to be able to engage in longer and more sophisticated verbal exchanges, to be able to have a conversation with us, and not just for performing simple tasks. So if this is what we want, then I'm afraid we have a long way to go, because definitely dialogue is not just a sequence of sentences. It's not just a matter of recognizing a sentence, producing or synthesizing a sentence, and looping. It goes way beyond that. So we need to understand so many different aspects of human dialogue, so many of them. Sometimes we're not even aware of the complexity of what we do when we have a conversation. So in our group, we are working on just a few of these challenges, and we are working along two main dimensions, which I will talk about next. One is improving the coordination between user and system. How we coordinate conversation is a tough task. And also, we want to be able to track the user's mental state during interaction, to know what they feel, what they think. So let's begin with a few of these research directions. I'll begin with turn-taking. This is related to coordination, to how we coordinate our conversations. We do this naturally. We need to be able to model this and incorporate them into dialogue systems. So say we have this problem. The user says something, some speech utterance, that ends at the end in a silence, a very short silence, maybe 200, 300 milliseconds, very short. And at this point, the system should be able to tell if it should wait, because the user will continue speaking, or start talking, because maybe the user is already waiting for an answer, which should come right away. Or maybe it should say, uh-huh, and continue listening. So these decisions have to be made really fast, right? We cannot let the user waiting for a couple of seconds, because naturalness goes, right? Yes, goes to, well, no. So this is a typical machine learning task. We can extract some acoustic features from some portions of the signal, typically to the end of the user input. Then we train machine learning models that are able to make the prediction that we need at that point. So this goes farther than that, and there's many other different tasks involved, but this is the main task for spoken dialogue systems. So let's move on to the second dimension, which is speech coordination between user and system, which is referred to this very amazing phenomenon called entrainment. This is something really exciting that we don't even notice when we speak. Entrainment is the tendency to adapt our speech and in general behavior, but let's focus on speech. So we adapt our speech to become similar to our interlocutor's speech. So we mimic our interlocutor. We do this all the time, and we don't even pay attention to this phenomenon. This is part of natural conversations. There's plenty of evidence in the literature, especially in the psychology literature, social psychology, that this phenomenon takes place at very different levels of communication, including lexical, phonetic, syntactic, prosodic, and others. But to make things a little more complicated, unfortunately, this is a very difficult phenomenon to model, because there are strong and complex interactions with social, cultural, and psychological factors. It's a mess. It's really difficult to understand when and how this takes place, but it does take place. It's something that we need to incorporate into our systems if we want them to sound natural, to behave in a natural fashion. So the question would be something like, after a user turn, how should the system adapt its speech next, based on all sorts of contextual features. So what are we doing about this? One of the lines that we're pushing forward is we're experimenting with toy spoken dialogue systems, typically small, very simple games. And we use each of these systems can use different strategies, different policies of entrainment. So we experiment with different policies, and we observe the effect on both the user, the interaction, and other outcomes. So we try to see how the system should entrain to the user. So let's move on to another line of research, in this case dealing with the tracking of the user's mental state. This is a more classical speech processing task. It's the detection of emotions. And we care about this because we do this in normal conversation. We want to know if the other person is angry, for example. We want to do something about it. And the system also, if it can detect that the user is angry for some reason, then it may want to do something about it. So this is a typical or classical machine learning task. It's a very difficult one. And main obstacle in this field is that there are very few data sets available. And these are often problematic. Some of these data sets have design issues or even contradictory or inconsistent labeling schemes. So it's a very difficult problem to work on. So we're training deep learning models for this task, and our current challenge is to mix these two guys, to fuse these two models together. One is a word-based model based on the transcriptions of the audios, which works at pretty much state-of-the-art level. And the other one is an audio-based system, which also works very well. But the question now is how to optimally fuse these two models to take advantage of the information in each of them. And finally, after we finish with this, project, the motion project, we will move on to detection of trust. In this case, we want to know how much the user trusts the system abilities. We want to know if the user trusts the skills of the system, right? As soon as you stop trusting the system's skills, you stop using it because it's useless. You won't be able to get help from the system if you don't trust how well it can perform. So this is something that is crucial to be able to monitor in the user, because as soon as the user stops trusting the system, then the conversation may end pretty soon, and the user will never come back after that. This is a novel task. No one has done this before, so that means there is no baseline, and even worse, we don't even know if this is actually possible. So can you detect trust from speech? I don't know. I don't know. So we want to figure out if this is possible. So for this, we're currently collecting a speech data set. We had to design a very carefully, a very difficult protocol, complex protocol for making subjects either trust or distrust the skills of a virtual system. So we're finishing, we're completing the collection of this corpus, and the next step will be, as I said before, trying to implement an automatic trust detector using the knowledge we've gained from the emotions project. Okay, so these are the people in the lab who are currently involved in this project. You may see some of the faces around here. Some of the guys are attending, Luciana, for example. And so I will be happy to answer questions. Thank you very much.
Thank you very much, Agustin, for this talk. We have time for one question. There.
So thank you for your talk, very interesting. Here. So I was wondering, what's your experience with like noise environments in speech, or do you work only with like clean audios where there's only speech and no like environment noise? And yeah, how do you deal with that?
We kind of, well, our experiments are done in a very silent environment, so with clean speech, but we kind of count that that will be the case, but ideally we should move on to building robust systems, right? So for the turn-taking experiments, for example, we try to develop both like perfect noise condition setups and also for noisy setups, so that we try to build robust versions of the systems. And in the entrainment scenario, we really need sound to be really clean, because the effects are so subtle that we are very far from understanding them. So no, if you add noise there, we would lose the signal completely.
Hi. How do you think about the develop of these models, prosody modeling, speech recognition, and artificial general intelligence? And
I'm sorry, I didn't understand.
The relationships about speech recognitions and not artificial intelligence, sino AGI, artificial general intelligence.
So the system, how do you mean how intelligent are these systems?
Yes.
Well, they are very dumb. They are very simple. They only perform simple tasks, such as, we simulate. We try to fool the user into thinking that the system can do much more than it actually can. So if it's playing a game, we try to fool the user into believing that the system is actually playing a game smartly, while actually we only have hard-coded rules. So we try to keep things as simple as possible to reduce the variability and control for all the different variables. So the systems are completely dumb, the ones we use. Then hopefully we will be able to then use these technologies into more intelligent systems.
Thanks, Agustín, again.
Thank you.